I will begin. Dear Father, we thank you for this day. Again, Lord, I thank you for these students who are with us today. Help us to, again, just to glorify you, what we do, Lord. In your name I pray. Amen. Okay, so today I am going to try to explain to you guys what the real Jordan form is. So we hopefully have some idea what the Jordan form is. That makes sense when we have eigenvalues for our linear transformation or matrix, and we have enough of them so that the characteristic polynomials split. But sometimes we're working with a real transformation, right? And we don't have real eigenvalues. So what do you do in that situation? Well, that's where the real Jordan form comes into play. And all of this is built over the notion of complexification, which we talked some about it already. So let me just review the basic ingredients of that, because we'll need those today. So what's the complexification? So here we're going to let V be a vector space over the reals, all right? And we're going to let T be a linear transformation from V to V, okay? So you could say this is a real linear transformation. What I mean by that, of course, is that it's a linear transformation of real vector spaces. All right. And so one of the things we described in the last lecture was that you can make up this thing called the complexification of V. And formally speaking, it's just complex linear combinations of real vectors like this. It's x plus iy, where x and y are themselves real vectors. So this is the so-called complexification of V. Complexification of V, it's a complex vector space. In other words, the scalar multiplication is that of complex numbers. In particular, the way we multiply a complex number, actually let me use alpha plus I beta, all right, and I'll do a plus IB here. Well, so here I'm assuming that A and B are real vectors, and on the other hand, over here, alpha and beta are real numbers, but that's a complex number, right? Because there's the I there. And that's a complex vector because there's an I there. And essentially, by definition or construction, we multiply in the usual way. So we get alpha A minus beta B plus I times alpha B plus beta A. So that's just what you'd expect if you just basically operate formally with the one sort of new weird assumption that I squared is equal to what? Formalism, to set I squared equals to minus 1. I mean, that's what I described last time. We can look at the Cartesian product, and that's this complexification here. And all right, so that's, again, the complexification gives us a new complex vector space. That's how we do the complex scalar multiplication. And then we also define a T sub C, the complexification of the transformation, which is actually a complex linear transformation from V sub C to V sub C. If you want me just to sort of emphasize this, double down on the notation, we have T is a real endomorphism. It's a real endomorphism of V, whereas T sub C is an element of, it's a complex endomorphism of V sub C. Is there music? I don't think I have music on my computer right now. And I just unplugged the computer. Well, that's new. I've had a lot of different problems over the years, but this is a new one. What is it? Here. Huh. Let me see if I can cover it up with something different. There. Okay. Well, I can make it. Okay. We're now listening to Final Countdown, but at a very low level, so. Yes. All right. So there now, I only hear the voices in my own head. That's better. Okay. So this is the complexification of t sub c, which is itself, it's a new transformation, but it's built from the old. All right. And how do we build it? Ah! Come on. Seriously? Well, I hope I don't get shocked or something today. I don't know. A little bit concerning. Anyway, so t sub c of x plus iy is by definition, guys, this is the complexification of t. So I describe here how to complexify the vector space. This is how we complexify the, see, I'm going to move this, but I regret doing it already. Okay. So it's just what it has to be. It's t of x plus I t of y. And this is for all x plus iy in v sub c. Okay, so this gives us the complexification of t, which is a linear transformation on the complexification, which is in fact a complex linear transformation, and obviously it is very much related to t. But it's not t, because it's got a new domain, it's got a new codomain, all right? So with this construction, all of a sudden it makes sense to talk about the complex eigenvector of a real transformation. So what do we mean? Complex eigenvector of a real transformation. So here's the definition. Definition, t from v to v has complex eigenvalue lambda alpha plus I beta and complex eigenvector, let's say v equal to a plus ib in v sub c if v is an eigenvector of t sub c with eigenvalue lambda equal to alpha plus I beta. So in other words, what I'm saying is that we can talk about complex eigenvalues and complex eigenvectors for a real transformation with the understanding what we're talking about is the complex eigenvalue and complex eigenvector of the corresponding complexification of t. And we can always make this complexification, so it's something we can always do. All right? So, first order of business then is proposition 8.314. And it says the following, for v, a real vector space, and t, an element of, it's a real linear transformation on v, for this and this, such that, let's say z equal to x plus iy, in the complexification is eigenvector with eigenvalue lambda equals to alpha plus I beta, with beta not equal to 0. So if that is a eigenvector with eigenvalue that with beta not equal to 0 for t sub c, then z bar, and you know what, let me change that to a plus ib, okay? Not x plus iy, but a plus ib, all right? Then z bar, which would be a minus ib, this is the so-called complex conjugate, is eigenvector with eigenvalue lambda bar equal to alpha minus I beta. In other words, if we have a complex eigenvalue and complex eigenvector for a real transformation, then there is a conjugate pair. There's a corresponding conjugate eigenvalue with conjugate eigenvector. They come in pairs, right? Here's the proof. So we're assuming, what are we assuming? Lambda is equal to alpha plus I beta. Beta is not equal to 0. And z is equal to a plus ib, which is not equal to 0, such that what? With, what are we assuming? T of, t of z is equal to lambda z, right? Actually, that's not what we're assuming, is it? That doesn't even make sense. Can I operate can I put a complex vector into the real transformation t? No, I cannot. So what I should have written there is t sub c, okay? It's the complexification's eigenvector. So what's this mean? This means that t sub c rather of t sub c of a plus ib is equal to alpha plus I beta times a plus ib. Right? But then by definition of complexification of transformation and space, we get t of a plus it of b on the left-hand side. And on the right-hand side, we get alpha a minus beta b plus I times beta A plus alpha B. All right. But by construction of the complexification, we have equality of both the real and the imaginary parts of a complex vector equation. Remember, they're like the x and y components of a two-tuple. We built it from the Cartesian product of v and v. And so that part of that really assumes that there's an independence of the real and imaginary components. So what I'm trying to say is this equation right here, right, it gives us two things actually. It gives us that t of a is equal to alpha a minus beta b. And it also gives us that t of b is equal to what? Beta a plus alpha b, right? This is from the real component. This is from the imaginary component of star. We actually don't even need that right now, but it's going to be, this saves us a little work in about 10 minutes, okay? Just saying, you can see that right here already. Now, I'm trying to prove something about the complex conjugate vector and complex conjugate eigenvalue. So what should I do to star, actually, to prove what the proposition I'm actually looking at here? I mean, this is a digression, okay? So put it up here, save for later. So we take the complex conjugate. How is that defined? in short, complex conjugation is when you take the I and change it to minus I, everything else being the same. Pretty much it. So when I take the complex conjugate of star, we get T of A minus I T of B is equal to alpha A minus beta B minus I times beta A plus alpha B. So that's by taking the complex conjugate. If you want to be more theoretical about it, the complex conjugate is an automorphism of the complexification. So we're taking this equation and taking, and operating by bijection on both sides, so we don't change the solution set. Anyway, so once you have that, you just undo what we did. So what this says is T sub C of A minus IB, because I can pull the minus inside T because T is linear, right? So using the definition of complexification T, that's T of A minus IB. And then also unmultiplying the other side, this is alpha minus I beta times A plus IB, A minus IB rather. So going from here to here, I'm just unmultiplying if you like. I guess we usually call that factoring. But the proof is in the pudding. I mean, if you multiply this out, what do you get? You get alpha A minus times minus I times minus I, which is I squared, which is minus 1, beta B, that term. And then we get minus beta A, and we get a minus alpha B. So you can see that that's legit. And then just notation. This is T sub C of Z conjugate is equal to lambda conjugate times Z conjugate again. And that proves that the complexification has complex eigenvector Z bar with complex eigenvalue lambda bar, right? So if we're just working with a matrix, there's an even easier argument, right? So like suppose A is an n by n matrix, right? And suppose you have V in Cn and lambda equals to alpha plus I beta, a complex number, such that what? Such that AV equals to lambda V, right? In other words, that's what we call a complex eigenvector for a real matrix, all right? In fact, you could argue more specifically here, V is actually an eigenvector for L sub A, the complexification of it, which goes from Cn to Cn. The complexification of Rn, remember guys, is Cn. So in fact, V is not an eigenvector for A, it's an eigenvector for the complexification of the left multiplication map by A. Ugh. Anyway, that's still just a complex matrix equation, so you can take the complex conjugate of it directly. What's the complex conjugate of a real matrix? I mean, we're assuming A bar is equal to A. That's what it means for A to be real in this notation, yeah? So we can actually prove that, a complex eigenvector has conjugate eigenvector V bar with conjugate eigenvalue lambda bar without all this extra stuff that I just did. In the case we're working with a matrix, there's an easier argument, which I just wrote in purple. It's direct matrix calculation in complexes. All right, so that's proposition 8.2.14. Why is this important? What can you tell me about lambda and lambda bar if beta is non-zero? Fill in the blank for me. I mean, they're both complex, sure. But one more. They're what? They're not equal. That's the thing. They're distinct. And why is that important? Thus, if we look at, z and z bar from last proposition form rather a linearly independent subset of the complexification of V, right? Because distinct eigenvalues gives us linear independence. And so that's one of the fundamental observations which goes into the next theorem. So here's the next theorem. This is 8.3.15. So again, for a real transformation, so V is a real vector space. T is a linear transformation from V to V, once again, with complexification T sub C from V sub C to V sub C, as usual. If this with this and, Z equal to A plus IB is complex eigenvector with lambda equals to alpha plus I beta, beta not equal to 0, then a couple things. Number one, A comma B, let's call that gamma, is linearly independent subset of the original vector space V sub r. In other words, it's a real linearly independent subset. I'm looking at two real vectors, A and B. These are the real and imaginary components of the complex eigenvector. Okay? I mean, you could, in fact, often the notation that's used, if you want notation to say what A and B are, in terms of Z, a typical notation would be this. The real part of Z is A. The imaginary part of Z is B. So both the real part and the imaginary part of this complex vector are separately real vectors. By construction, in fact. So point number one, if we take the set with A and B, it's linearly independent. Point number two, the span of gamma, if we call that W, is T invariant subspace of V. All right, that's nice. And then three, the matrix of T with respect to this invariant subspace and that basis gamma is, in fact, just alpha beta. Well, there's alpha minus beta for the first and beta alpha for the second column, like that. By the way, that is an example of a real Jordan form. This is really the fundamental building block of the real Jordan form. What makes it new, anyway? Real Jordan form, after the dust settles, should be an amalgam, a combination of both the Jordan form we've already looked at and this new thing we're discovering today, which you've seen in homework before because, well, that's what I do. So let's see here. Before I get into the linear independence, can you see how we've already proved 2 and 3 by calculations on the board? What would T, suppose, just bear with me, put the cart before the horse, so to speak, assume linear independence of gamma, suppose it's a basis, right? Can you, if you look at, say for later, this shows that the image of A and B under T are again in the span of A and B, right? So this calculation right here shows you T invariance of the subspace W. And what does this mean? What is this? this says that the gamma coordinate of TA is what? And what's the gamma coordinate of TB? If gamma, again, is this right here. A comes first, B comes second. So if I have alpha A minus beta B, the coordinate vector is alpha minus beta. And if I have T of B is beta A plus alpha B, the coordinate vector is beta alpha. So then by our usual song and dance, what's the matrix of T sub W with respect to the gamma basis? Well, it's the coordinate vector of the first thing in the basis, and then the coordinate vector of the second thing in the basis, which is exactly this 2 by 2 matrix. So that's the proof of 2 and 3. All that remains for us is to prove linear independence of A and B, right? I was very lost on this in one point in a general faculty meeting about 5 years ago. But then there was a professor here at that time, Dr. Honoré Mavinga, and he helped me with it. So it turned out to be a good faculty meeting after all, because I figured out how to prove linear independence of A and B. And I'll share that with you now. I feel like a faculty meeting is only worthwhile in as much as you can do math in it, right? I mean, you're not there yet. Maybe for you it's, well, I can't say. Psychology of relationships. Let's say psychology of relationships. Maybe you need to do. Wait, are we still doing that course, you guys? You're still in there? Still real? Was it helpful? Do you understand people better for it? Can you? It's not required anymore. So, are you taking other courses to learn how to bend people to your will? No. That's not what that course is for. It's here. I still think my advice to avoid excessive wooing in relationships early on is more useful, probably. But anyway, all right. So I need to erase something so we can work. So how do we show linear independence of A and B, guys? So what we should do, I'll do it here. If we suppose C1a plus C2b equals to 0, right? And this is for what? C1 and C2 where? Reals. We're trying to prove A and B are linearly independent with respect to the real vector space structure. So we take a real linear combination, we set it equal to 0. Now it's up to us to prove that A and B, that forces C1 and C2 to be 0. Notice that, let's see here, A is actually equal to, well, step back a second here. Z is equal to A plus IB, right? Z bar is A minus IB. So you can solve these for A equals to 1/2 of Z plus Z bar, right? If you take Z plus Z bar, what do you get? You get 2A, because the IB and the minus IB cancel, right? What if you subtract them? Subtract Z from Z bar. What happens then? You get 2I times B, right? So 1 over 2I times Z minus Z bar is equal to B. Just algebra. Now plug those formulas into our equation star. So substituting into star. And we get C1 over 2 times Z plus Z bar plus C2 over 2I Z minus Z bar equals to 0. All right? But then what should I do? What do I have to work with here? What's the real reason that A and B are linearly independent? It's because Z and Z bar are complex linearly independent, right? So what I should do is I should repackage this. This is really 1/2 of C1 minus IC2 times Z plus C1 over, well, excuse me, plus 1/2 of C1 plus IC2 times Z bar equal to 0. If that seems like dark magic, what I just did, you should know that 1 over I, weirdly, is equal to minus I. If you haven't worked a lot with complex numbers, you might not know that, but that's true. Think about it. If I squared is equal to minus 1, that means that 1 over I must be equal to minus I. Right? So I use that. That's where the minus IC2 and the plus IC2 came from here. But then, by linear independence, by the remark, right? Thus, by linear independence of Z and Z bar in V sub C, we find that, well, we can drop the half, right? C1 minus IC2 equal to 0, and C1 plus IC2 equal to 0. I could divide those by 2 if it makes you feel better, but I'm just not. I'm tired of writing. And then what happens if you add those equations? What does it yield? Adding these yields 2C1 equal to 0, which then tells me C1 is 0, which tells me that C2 is equal to 0, and we're done. Right? Because now we've proved linear independence of AB. Consequently, AB is a basis, W is an invariant subspace, and that's its matrix. Es bueno. Well, anyway. Okay, so what else is out there? What if we had a real transformation on a 4-dimensional real vector space, right? Suppose V is 4-dimensional for the sake of discussion. Or consider the dimension, the real dimension of V being greater than or equal to 4, such that V1 and V2 are in the complexification of C such that, here we go, T minus lambda, well, T sub C rather, minus lambda of V2 is equal to V1, and T sub C minus lambda of V1 is equal to 0. In other words, suppose that V1 and V2 form a 2-chain with complex eigenvalue lambda for the complexification T. All right. So here, V1 is eigenvector, and V2 is generalized eigenvector for T sub C. Now, of course, I want to think about, again, we're given T from V to V, right? And so that gets us to the complexification from the complexification. So I'm still talking about a linear transformation on V sub C, which arises from a real transformation T. It's the complexification, right? Since I'm doing that, we can still go through pretty much the same complex conjugation argument I already did. I won't go through the details, but, well, I mean, we've already gone through the details to prove what? Like this also gives you what? And this I haven't gone through the details, but you could easily calculate that T sub C minus lambda bar acting on V bar 2 is equal to V bar 1. So if the real dimension of V was 4, that would say that the complex dimension of the complexification was also 4. But it's a 4-dimensional complex vector space. And the complexification being this 4-dimensional complex vector space, if you could give a basis gamma, you could form the basis, you know, V1, V2, V bar 1, V bar 2. And by our usual Jordan form stuff, what would the matrix of T with respect to this gamma basis look like? Well, the matrix of the complexification of T, actually. It would be J2 lambda, direct sum, J2 lambda bar. Because we have two chains, that would be what I mean, so it's a 4 by 4 matrix, which has got lambdas or lambda bars in the diagonal and ones on the super diagonal. This is not the real Jordan form. My point to you is that the complexification has a complex Jordan form. All right? So what's the real Jordan form? Well, the real Jordan form is for the original transformation T. I need to find a place. I guess I got to write over here. Bad planning on my part. Okay, so so we just need to, so we need a little bit more letters. So let V1 be A1 plus IB1, and we'll let V2 be A2 plus IB2. And instead of calling this, let me call this gamma tilde because I don't really care about it. All right. So what I want to argue, I'm going to argue that gamma equal to A1 B1 A2 B2 is nice choice. I want to try to explain to you why that is. We could prove linear independence through arguments similar to the ones I've already given. All right, I won't go through that, but you could prove linear independence of A1, B1, A2, B2 from what's on the board. So it is a basis. And then the question is, what does the matrix of T look like in this basis? So we already kind of know part of it, right? Let's see here. So T, we know that T of V1 is equal to lambda V1, right? Let's suppose lambda is alpha plus I beta. All right? So what's this tell us? This is just that, again, T of A1 plus I T of B1 is equal to alpha plus I beta times A plus IB1, A1 plus IB1. And so here it is again, alpha A1 minus beta B1 plus I times beta A1 plus alpha B1. Okay, so again, this is a complex equation, so we get that this has to match that. But we also get that the imaginary component has to match the imaginary component. I'm really not doing anything new here, but what this shows is that the coordinate vector of T of A1 is what, with respect to the gamma basis? Reminder, I wrote the gamma basis right here. Can you guys tell me? We're looking for four-dimensional real vectors. Can you read? Yeah, alpha minus beta. How many copies of A2 and B2 do we got in here? 0, yeah. So I'll do that over here. And this one? Beta alpha, right. Now we just need to translate what that other, this is the weird new piece right here, right? So we need to focus on that, figure out what that does. What is that complex, generalized complex eigenvector for the complexification words look like? All right, so this means that T of V2 is equal to lambda V2 plus V1, right? So that's T of A2 plus I T of B2 is equal to alpha plus I beta times A2 plus I B2 plus A1 plus I B1. So we get T of A2 plus I T of B2 is equal to alpha A2 minus beta B2 plus A1 plus I times beta A2 plus alpha B2 plus B1. So now we can read from that what the coordinate vectors of T acting on the last two things in the basis are. So what's the coordinate vector of T of A2 with respect to the gamma basis here? T of B2 with respect to the gamma basis. What's that? So we got one copy of the first thing, right? So that this A1 puts a 1 up here. We have no B1, so that's a 0. We have alpha A2s. We've got minus beta B2s, so there you got that. Over here, I've got no copy of A1. I've got one copy of B1. I got beta copies of A2. I got alpha copies of B2, so there you go. Again, all I'm doing is using the definition of coordinates and basis yet again. Okay. So put this all together, what's the matrix of T with respect to the gamma basis? I'm just assuming T is acting on a four-dimensional real vector space to avoid myself extra writing. You could suppose it's acting on a larger space. This would be an invariant subspace on which your matrix would have this form. So anyway, focus. So what's the matrix here? It's alpha minus beta 0, 0, beta, alpha 0, 0, 1, 0, 0, alpha minus beta, 0, 1, beta, alpha. So you see, there's some kind of cool pattern going on here, isn't there? We've got these blocks, these fundamental blocks that seem to be making up the Jordan form, and a copy of the identity matrix. Now, so here's the way we can rewrite this. There's a notation which I have not told you guys about yet, but it's going to be super useful for us. So this on the one hand is alpha beta minus beta alpha, zeros, 2 by 2, 0, 2 by 2, 0, alpha beta minus beta alpha, and then plus, what do we got? We've got 0, 0, 0, the identity matrix, right? So it's the sum of these two 4 by 4 matrices if you look at it. So we can rewrite that in terms of something called the Kronecker delta, well, the Kronecker product, not to be confused with the Kronecker delta, of course. I mean, same Kronecker, different thing, but anyway, so what we got here in terms of the tensor notation is 1, 0, 0, 1, tensor, alpha, well, oh, one second. Yeah. Tensor alpha beta minus beta alpha plus, and then this one is 0, 1, 0, 0, tensor the identity matrix. Well, tensor I. Well, fine, 2 by 2 I, 1, 0, 0, 1. If you had a complex eigenvalue repeated 3 times, all right, for a real transformation, and if you had a 3 chain of complex eigenvectors, then what you end up with is the tensor product of the 3 by 3 identity matrix with this 2 by 2 block plus the nilpotent thing of order 3. This is the nilpotent thing of order 2. I mean, this matrix 0, 1, 1, 0, 0, when it squares to 0. Like the fundamental thing which cubes to 0 but squares not 0 is, well, the next thing up the chain here would be 0, 1, 0, 1, 0, 0, 0, 0, 0. This 3 by 3 matrix, square is non-zero but cube is 0. In fact, if you go back to the Jordan form we looked at before, there's something I really should point out to you guys. One of the beauties of the Jordan form is that it provides us this decomposition. So what's it look like? I mean, suppose we're looking at the k by k Jordan block of lambda. We got what? We got lambda, lambda, da-da-da, lambda, and then you got ones, right? Zeros elsewhere, right? So you can rewrite that as lambda times the k by k identity, right? Plus, we might call it n sub k, where this n sub k is nilpotent order k. Right? I mean, this is what the Jordan form is. It's a decomposition of the matrix into a diagonal part and a nilpotent part. And so if you're thinking about doing calculations with the matrix, having this decomposition is actually very, very simplifying. And you can prove furthermore, you can prove that, well, I mean, this and that commute. For example, if I was to calculate the matrix exponential of the Jordan form, I could easily look at that as the matrix exponential of lambda times the identity plus the nilpotent piece. And so it would give you e to the lambda it and e to the nkt. Now, if you haven't had differential equations, you know what I'm talking about, and that's okay. I'll come back to this later when we have more time. But when I have more time to tell you talk to you about this in more detail, the point of this formula is that since n sub k terminates at finite order, past the kth power, it's 0. This matrix exponential is defined in terms of like an infinite series, just like exponential. I guess I can afford that much. E to the a is the sum n equals 0 to infinity of a to the n over n factorial. This is so-called matrix exponential. And so long story short, this exponential of a nilpotent piece is a finitely calculable thing because this truncates at finite order at k. And on the other hand, this actually just gives you the diagonal matrix with e to the lambda t on the diagonal. So the matrix, the Jordan form makes the matrix exponential very straightforward to calculate. This is still true for the real Jordan form, but their sines and cosines appear, so it's more complicated. But all right, so let me try to stop digressing and finish. Oh, come on. Of course, my computer was not actually, I mean, you'd think it was plugged in because I had the plug plugged in, but of course it's my computer, so the plug has unplugged itself. I just wanted to show you guys like one or two things before we stop here today. So in summary, the real Jordan form, so what I haven't showed you yet is we have, of course, some real matrices don't have just complex eigenvectors, right? They've got some real eigenvectors. They've got some complex eigenvectors. The real Jordan form is an amalgam of that. You just do the regular Jordan form thing that we already did for the real eigenvalues. Those give you real Jordan blocks. And then whenever you get a complex eigenvalue, you find the corresponding complex, the so-called real Jordan form, which is what I've showed you how to find today from the complex eigenvector. And so, oh, yeah, I guess I should actually plug it in. Sorry about that. Oh. Which 8? Wrong 18. Can you see linear algebra? Oh, there it is. I should have warned you to take your medication before this. Let's see here. Come on. I guess I could actually just search, right? Oh, there it is. In my defense, I had it opened up to precisely the page that we were supposed to look at, but then you know what happened. Come on. This is what we just went through. So we basically just derived, can you, it's fine, I'll just, so we basically just derived this theorem, the 4x4 Jordan block, real Jordan block. And so, again, this is, I use gamma tilde here to express this idea. This is what, if you had a 3-chain for a complexification, this would be the sort of analog of the gamma tilde thing I did today. Because remember, they come in conjugate pairs. The corresponding real Jordan form for the third order case gives you a block, a block, a block, and then one's identity matrix on the upper blocks. It's kind of a little bit non-intuitive. But again, this formula is the one we found. And the next thing up looks like that. So the next thing up would be this. If you had a 3 repeated 3 times, this. If you had it repeated 4 times, it would be this. That will never happen to you, I don't think. But these do come up in differential equations because we have problems with repeated complex eigenvalues. And I think that's pretty much all I got for you guys. This section here, you can read lightly. This is the stuff that bonus questions is born of. I mean, there is hard stuff in this section, but interesting. And we'll pretty much be skipping over it this semester. So next time, I will talk to you about geometry. So thanks, guys.